Today we're going to do the central limit theorem and how it relates to normal calculations. So let's get started. Okay, so the central limit theorem basically deals with sample means. And given any population, it has a mean mu and a standard deviation sigma. And we take random samples of size n. Then what happens is the distribution of sample means becomes normal. That's pretty cool. The second thing is that the mean of the sample means is about the mean of the population. And the third thing is that the standard deviation of sample means decreases by square root of n. So the central limit theorem deals with what happens when you take samples of a population and you look at the means. The means are normally distributed, and the standard deviation of the sample means shrinks by a factor of square root of n. Have a look at it. So looking at the central limit theorem, take any population, this is kind of a skewed distribution, and we're going to take samples of size n is equal to 10. And we're going to take a look at the distribution of sample means. If we take 1,000 samples of size 10 and look at the means, what happens? We get a distribution that looks like this, and it's fairly normally distributed. If we take a sample of size 20 and do it again, if we just take 5, we get this, but if we take 1,000 of them or 10,000 of them, we get a distribution that looks like that. That's pretty normal. It's pretty normal distribution of sample means. Okay, so basically sample means, the distribution is normally distributed. The mean of the sample means is the same as the mean of the population, but the standard deviation shrinks by square root of n. Let's see how this comes into play with calculating normal calculations. All right. Well, heights of North American women are normally distributed with a mean of 64 inches and a standard deviation of 2.1 inches about. So first question, what is the probability that a randomly selected woman is taller than 67 inches? Well, that's our normal calculation. We calculate our z-score and we get 1.43. So what's the probability that is taller than 67 inches? So that'd be from this z-score out to infinity. So we use our normal CDF, 1.43 to 8, and we get this. Now, the big difference is, say we took a random sample of 4 women. What's the probability that the average of those 4 women, the sample mean, is greater than 67 inches? Well, now our z-score for sample means is x bar, the mean minus the mean of the population, divided by the standard deviation of x bars. Well, the standard deviation of x bars by the central limit theorem is sigma divided by square root of n. So we get this square root of n factor. So for sample means, your z-score is calculated as, well, same thing, 67 minus 64. But now it's divided by the standard deviation of sample means, so 2.1 divided by square root of 2. And we get a z-score, pretty large z-score, of 2.86. So greater than 67 inches, so it's 2.86 to infinity, and we use 8 for infinity, 8 standard deviations away from the mean. On a normal distribution is essentially infinity, at least for our precision of probability. So normal CDF is equal to maybe 0.2% or 0.00211. Okay, let's do another example. What is the probability that the mean height of a random sample of 30 women is 63 inches or less? Okay, well, same thing. We have to divide by the square root of n, but in this case, n is equal to 30. So we have 63 minus 64, the mean, divided by the standard deviation, divided by square root of n, the standard deviation of sample means. So we get a minus 2.61. So normal CDF or less, so minus infinity up to 2.61, and we get 0.00435. Let's see one of those on the calculator. So if we go to second distributions, we go down to 2 normal CDF, and we put in -8 from minus infinity, comma, to a negative 2.61. Again, we have to use this negative sign down here. Close parenthesis, we hit enter, and we get a 0.0045 rounding to 3. Okay, well, I hope you found that useful for learning this material, and I hope you enjoy your learning. Cheers.